16.2 second order homogeneous linear differential equations. Okay, that's a mouthful, so we're going to break that down. So in 16.1 we saw something like dy dx is equal to kx. This is a differential equation because it contains a derivative. Just make sure that's focused. Now, this is a first-order differential equation because it includes a first derivative. So we can a lot of times I'm going to rewrite this as instead of dy dx, y prime equal to kx. Okay, that's a first-order differential equation. The second-order differential equation might look something like this: y double prime plus, and then you might equals, but plus, let's say 3y prime minus 8y equal to, could be equal to something else, sine of x. This would be a second-order linear differential equation. Okay. In general, you could have things a lot more complicated than this. You could have something like, let's say 2x y double prime. So these different orders of derivatives, these different derivatives can have functions in front of them, functions of x as coefficients to them. Okay, so plus, and you could have something like a sine of x in front of your y prime, and then let's say minus e to the x y. And then you could simply have another function that doesn't have a y prime, or y double prime, or y triple prime. It could be third order or fourth order. Second order here because it has a second derivative equal to 0. Okay? Now, you can always move this thing over to the other side, and then you can always, what we're typically going to want to do is divide everything by this function that's in front of your highest order derivative. So the first thing we'll do, we'll move this to the other side. That becomes an ln x. And then we're going to get rid of the 2x. So that's not going to be there anymore. We're going to have y double prime plus, this is now going to be sine of x over 2x y prime, and then minus e to the x over 2x y is equal to this. Okay, this is a really messy one I just kind of made up off the top of my head, but this is a second order linear differential equation. Okay, now we have the word homogeneous. If this over here is a function, it's non-homogeneous. But if this over here is 0, that makes it homogeneous. So we have y double prime plus sine x over 2x y prime minus e to the x over 2xy. This thing right here, if it's equal to 0, then we call it homogeneous. This over here, where we had it not equal to 0, was non-homogeneous. Okay. So in general, the general form for a linear differential equation would be the nth derivative plus some function, we'll call it g1 of x, times your, then you go down by 1 degree n minus 1. Of course, you don't have to have all the orders here. This is the general form. g2 of x, y to the n minus 2, plus dot, 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 and then you get down to g n minus 1 of x, and then you've got a y prime plus g n of x times your y is equal to some function here, x, f of x. Okay, and again, if f of x is equal to 0, then we call it homogeneous. Okay, we call that a homogeneous linear differential equation. Okay, now that would cover, if we tried to figure out how to solve all of these, that would cover the entire course. So we're only on section 2 of an intro to the course, so we're going to really simplify things. First of all, we're going to make it homogeneous. We're going to make this thing equal to 0. Okay? Second of all, we're going to only have a second derivative. Okay, so we're not going to have a fourth, fifth, or sixth derivative. It's going to start with, it's going to have the y prime, and a y double prime. So we're going to have a y double prime plus, and you could have some function of x, but we're going to simplify it even further. So these g of x's are going to be constant. So ay prime plus by, and then we're equal to 0, which makes it homogeneous. Okay? So we've really simplified these for the very beginning intro to this, the first section of the intro. So we're going to start with solving this, which is the second order because it has a second degree, homogeneous because it's a zero, linear, and also we simplified it further because we don't have these functions of x multiplied by our different various derivatives. Okay. Now, as we go through this, there's one more definition I want to explain to you because we're going to use it in the next theorem. Okay. And that is something called linearly independent. Okay. So two functions, let's say y1 and y2, are considered linearly independent when they differ by something more than a constant. And I'll give you some examples. Okay. So if you have y1 is equal to 5 times e to the x, and y2 is equal to x squared. These are linearly independent. You can't multiply the first one by a constant to get the second one. Okay? If I have something like 3x, y1 equals 3x, y2 equals, let's say, 3x squared. These would also be linearly independent. Okay. On the other hand, if I have y1 is equal to 5 sine x and y2 is equal to 7 sine x, these are not linearly independent. We call them linearly dependent. Okay? And I'm going to talk about that next because we're going to go right into the theorem. Okay, and just refreshing your memory. When we solved one of these, do you remember what the solution looked like when we solved one of these? It was actually a function. It was y equals something. Okay? So when we solve this, our solutions are going to be functions. They're going to be y equals some function of x. That's what our solution looks like. Our solution is any function y where we take that function y, take its first derivative, multiply by a constant, and take its second derivative, and add those together, somehow we get 0. Okay? So, let's talk about that next theorem. This is theorem 16.3. Okay. Theorem 16.3, which says if y1 and y2 are linearly independent, they have to be linearly independent, that's important. Solutions to your equation y double prime plus a y prime plus by equal to 0. Okay. Then the general solution to your differential equation is y equals c1 y1 plus c2 y2. As long as y1 and y2 are linearly independent, you can take constant multiples of both of those and add them together. And not only is this also a solution, it's actually also the general solution. Okay? So, in the general solution, that means it covers all possible solutions to this equation. Okay? So, I wanted to take a look at something and show you just an idea of what this looks like. So I'm gonna, if we look at this right here, this is from another book. We're not going to go through this example, but let's say we're solving this equation right here. Okay, y double prime plus ay prime plus by equal to 0. That's the type of thing we're going to solve. Your solutions are functions of x, are functions in the term of, in terms of y. And if we can find two solutions, y1 and y2, here it's going to be f and g, and you take f times any constant plus g times any constant. Okay, so this would be C1 is 5, C2 is G, you get that curve. C1 is 1, C2 is 5, you get that curve. C1 is 1, C2 is 1, you get that curve. Here C1 is negative 1, C2 is 1, you get that curve. Okay, this is a family of curves. Notice you could make an infinite number of these curves because C1 and C2 could be an infinite number of constants. But all of those curves will be solutions to this equation. That will cover all possible general solutions to this second order linear homogeneous differential equation. Okay. Okay. And we're going to go through a partial proof of this theorem. Okay. So let's say that y1 and y2 be particular solutions to our second order differential equation. Differential homogeneous equation. Okay, this one. So we're saying that y1 and y2 are solutions to this. What we want to prove is that this is the general solution. The first part we're going to prove is just that this is also a solution. Okay? So if y1 and y2 are both solutions to this, we can plug in y1 for y, y1 prime, and y1 double prime. We get y1 double prime plus a, y1 prime plus b, y1 would be equal to 0. We can also plug in y2, y2 prime, and y2 double prime. And then we're going to add these together. Actually, before we do that, we're going to multiply each of these by a constant, C1, and this one we're going to multiply by C2. Okay, so this distributes to everything. So we've got this term. Of course, we're going to have that one and that one, but we're first just going to take these two and put them together. C1 y1 double prime plus C2 y2 double prime. Okay. Now I'm going to go to the second term. And both of these are going to have an a in them, so I'm going to factor out the a. And I'm left with C1 y1 prime plus C2 y2 prime. Okay, then I'm going to do that. I'm going to distribute the third part. Both of those have a b, and I'm going to factor out the b. And I get C1 y1 plus C2 y2, and that's going to be equal to 0. Okay, because we set that equal to the right side, which would be C1 times 0 plus C2 times 0. Okay, now if you'll notice, look at what we have here. If we call this thing y, then y prime would be this, the rules of derivatives. The derivative of this would just be this. That would be y prime. And the derivative of this would be this. So this would be y double prime. And what we've shown is that this y, which is C1 y1 plus C2 y2, is also a solution to our general, to our second order differential homogeneous equation. Okay. Now the second part of that proof, that it's actually the general equation and it covers all possible solutions, unfortunately has to be left to future math classes because we don't know enough yet to